All right, so this is just a finishing up of the 7B1 note that we needed to do in class today, looking at the z-scores and the z-chart. So just to recap kind of what we learned in class, if we take any set of data that's a bell curve, so remember it has that nice symmetric bell shape. If we have our mean and we know our standard deviations, which means we could add, remember, to find those blue marks across both sides. Remember, we learned about the empirical rule that said we could go 1 standard deviation on either side, or 2 or 3. And that was those certain specific percents. But we learned that that doesn't give us information about anybody that falls in the middle between those bars. So if we standardize our normal curve and let the mean be 0, and we have a formula that's, remember, called the z-score formula. If we use that to convert our item to a number between -3 to 3, sometimes it might be a little bigger or a little smaller than that, because remember, we do have those little tails, then we can use a z-chart table for probability to find specific percentages, or decimals is how it comes, of probability for how many people are less than an item or greater than an item. So that was kind of the big setup. We said that we would go back through and do some of these. So this is our formula. Remember your Z, so the way you take any set of normal data, which means bell-shaped, and you convert things to z-scores, is you take your item in question minus the mean they gave you, and you divide it by the standard deviation. That's what puts it on this position of a placement on this bell curve, where we have these nice numbers and we have a table chart that we can read for this. Okay, so that's the big gist on that part. So let's go through and finish up some more, just converting things with the z-score formula. So if we look at this one right here, number 2, it says the driving speeds on a 2-lane highway are normally distributed. So that part is important. We do need to know we have a bell curve, because that is the symmetric shape. So normal, when they say that, they mean bell or symmetric. That's what that means, okay? The mean is 55 miles per hour. Standard deviation is 4 miles per hour. A driver, so now we're talking about a specific person, not just everybody. A driver is pulled over for driving too slow on the highway. The state trooper recorded the driver's speed at 40 miles per hour. So this is our data item in question, okay? What is the z-score of that speed? So we would take the item in question, which is 40, minus the mean they gave us, which is 55, and divide that by the standard deviation they gave us. So 40 minus 55 is -15. I usually go ahead and write that down. Divided by 4, and that is -3.75. Now that is way off the chart, right? So yeah, I think this person is driving unsafely slow for the place that they are at. They are way below this -3 mark. Remember, most people would be driving in the -3 to 3 range. That would be 99.7% if we look at the empirical rule of our drivers. So this person's way below that. So they are definitely driving at that would be a mark that I would say that's abnormal, and maybe we should check on that person, okay? So the test scores on a test were normal. So remember, that means symmetric, with a mean of 100 and a standard deviation of 15. A student at random scored 115. What's the z-score for that student? So remember, we take our formula. The student in question had 115. The average for the whole class was 100. And the standard deviation was 15. So this is 115 minus 100, which is 15, over 15. This is 1. So this person is exactly 1 standard deviation above the mean, which we would have gotten that if we'd done the empirical rule, because we would have had 100 plus 15, and 115 would have been one of the marks that we would have created. But look, the z-score tells me that too. This person is exactly 1 standard deviation above the mean. It's above because it's positive. Whereas this one, the person was below the mean because it was negative, okay? The birth weights of newborns at a local hospital have a normal, so that means symmetric, distribution with a mean birth weight of 6.3, standard deviation of 0.5. A newborn chosen at random weighs 5 pounds. How many standard deviations above or below is that 5-pound baby? So remember, standard deviations above or below directly relates to your z-score, okay? So z-score is equal to the actual baby in question, which is 5 pounds, minus the average for the babies, which is 0.6 or 6.3, divided by the standard deviation of all the babies. So 5 minus 6.3 is negative 1.3. I like to write that in there. Divided by 0.5 is negative 2.6. Now, when you have a question like this in Newton, you always answer the z-score part with the actual sign. You would say the z-score is negative 2.6. The interpretive sentence is always a number, which is the absolute value of this. So we're saying we are 2.6 standard deviations. That's what the z-score measures. You're 2 and a little extra above or below the mean, okay? The negative and the positive answer, like that is the words above or below. So since this one was a negative z-score, we are below the mean. So you only put the negative symbol on the one that says z equals. This is how far are we, and the below or the above word is going to indicate if this was negative or positive. So this is just an interpretive sentence, okay? So let's do another one like that. The test scores in a chemistry class are normally distributed, so again, they're symmetric, with a mean score of 75%, standard deviation of 9%. A student chosen at random has a score of 93. Is this an unusual test score? Calculate and interpret the z-score. So unusual, you have to look at their kind of structure down here. They actually kind of give you a hint about what that means. If you are more than 3 standard deviations, so notice if I'm, and this one specifically measures as, they say unusual would be more than 3. Because if you think about it, it's just like that one that a person was driving, right? When they were driving and they were driving super slow, they were at like negative 3.75. These are typical for this problem. They're saying 3 standard deviations. I got that directly from down here. 3 standard deviations is typical. So if we're beyond that in any way for this problem, that is considered unusual, okay? So I'm basing that purely on this setup in this problem below, okay? So let's find the z-score. So this person tested a 93. The average for the class was 75, and the standard deviation was 9%. So 93 minus 75 is 18, divided by 9 is a 2. So the z-score is a 2. A test score of 93%, I would say, is not unusual because the standard deviation is not more than 3 standard deviations, because 2 is actually right here. We're at the typical range. It's not more than 3 standard deviations. Now, this again has to do with the sign of your number. If you have a positive 2, we would choose the word above. If this had come out as a negative 2, that's still typical. We're still in the range they kind of gave us for this. So either way would have been fine, but we would have chosen the word below for this part. Okay, so above and below have to do with being positive z-score or negative z-score. All right, let's look at this one. So this says the average number of customers who eat at Grady's Grill is 300 per day. So that's the average. So that's the mean. Standard deviation is 45. One day they had 390 customers. So this is our data item. Calculate the z-score for that Saturday's crowd and determine if it's unusual. Now be careful. Newton sometimes switches from 3 standard deviations being normal to 2. That's because both of those are in that 90-something%, 95% for 2 standard deviations, 99.7% for the 3. So they consider anything outside of either of those to sometimes be atypical, but the problem will set that stage for you. So in the first one, they were marking it as if you're outside of 3 standard deviations, that's unusual. In this specific one, notice they've marked it as we don't want to be outside of 2 standard deviations, okay? So if we do our z-score, we would have 390 customers on that specific day. The average was 300, and that is 45. So that would be 90 on top, divided by 45. that actually equals 2. I think I wanted that to be a different number. Let's change this to 395. I wanted it to fall. I didn't mean for it to fall exactly on the number line because that's kind of you could go either way. So let me change that real quick. So 395 customers on that day and then divided by the 45 because I wanted it to be very clear which side it was on. So 395 minus the 300 is 95 divided by 45. And then this one will actually be outside of the 2. Yeah, so this is 2.11 for that z-score. So the z-score for that crowd was 2.11 because we usually round those to 2 decimal places unless they say otherwise, which is 2.11 standard deviations above the mean because that is a positive z-score. This is unusual for this specific problem because they said we want to be within 2 standard deviations, because the number of customers who ate at Grady's Grill is not within the 2 standard deviations of the mean, okay? So that's, you just have to be careful. So when we read this, it says a test score of 93% is not unusual because the standard deviation is not more than 3 standard deviations above the mean. With this one, they worded it a little differently. They said within, so look, this is unusual because we said if it's outside of a 2 on either side, so -2 to 2, that would be unusual. So this is unusual because the number of customers who ate at Grady's Grill is not within the 2 standard deviations of the mean. So they just worded them slightly different, so you do have to read these carefully. All right, so then that takes us to the last piece that we just barely got to start in class, which is using z-score conversions, which what we just practiced, to then find probabilities for any data item using the z-score probability chart. Now, if you have things that fall nicely on your standard deviations, so like if you have your mean and you have numbers that are exactly on the 1, 2, 3, the -1, -2, and -3, any of those exact numbers, they could have been done using the empirical rule, but it's more accurate to use the z-score chart, okay? So that's why I was saying in class, you just have to really realize that empirical rule is a nice rule, but it's not going to solve every single problem. So the z-score table is actually a lot more accurate. And then just to remind you about the table, it only gives you probability to the left. So when you look up your z-score, you'll always have your number, comma, or excuse me, decimal number. So your z-score, remember we said they're usually a whole number and then 2 decimal places. That's what we round to. So you'll always be looking up this part in the column part, and then the second or 100th part is in the columns over here, okay? And that goes all the way up to 0.09. So you have to find what are your numbers that you're starting with for your whole number and your 10th place, that's in this part, and then your 100th place is along the columns across the top, okay? We find where that overlaps, and that is our probability, but it is always the probability to the left of our item, okay? So your table gives probability to the left. If you want probability to the right, you have to remember that, so say this gives me let's say 3019, then this is 1 minus 0.3019. So just as an example, so if I want to go to the right, I always do 1 minus the value I found in the table, okay? So let's do some more examples together. So I did the first ones here. Let's look at the next group. So for number 9, it says find the probability of scoring below or to the left of a z-score of 1.42. So to the left is less than. Less than is always directly from the table. So left is always a direct table answer, okay? So we're going to find 1.4 and 0.02, and then we circle where that row and column overlaps. So that is how you do to the left. It's the easiest kind to do, okay? Now we want to know what's the, and again, there's a picture that goes with that. If you imagine being at, here's the mean, here's about 1.42 above the mean. To the left is this area. So it is a large area. It's almost all of your data. okay? To the right, we would want to do, if we look at the same graphic right here, to the right, we'd want to go this way. So this one is 1 minus the 0.922 since it's the same z-score. So if we look at that, 1 minus 0.9222 is 0.0778. Okay, so probability that we're greater than 1.42 or to the right is 1 minus the probability we were less than. Okay, so notice these two, if you're going from the same direction on that z-score, 1 to the left and 1 to the right of it, notice that should add to 100%. Okay. If Erica's exam score is a z-score of 1.35 and the data was normal, they're just telling you you can use the chart. What is the probability that a random student scored higher than Erica? That's another thing. You have to read your z-score and you have to know if you're going higher or lower. So this is asking probability that we have someone scoring better than Erica, so greater than. So we're going to be doing 1 minus whatever probability we find for 1.35. So 1.3 is this, 0.05 is the hundredths place. So that's going to be, this amount is the less than area. So the greater than her score area would be 1 minus that. So 1 minus 0.9115. So only about 8, there's a 0 there. Only about 8.85% of students scored higher than Erica. Okay. Determine the area under the standard normal curve that lies to the left, so less than 1.44. So Z, probability that Z is less than 1.44. So these are already in Z-score form. We didn't have to convert any of these. So if I look for 1.44, there's 1.4, 0.04, that's this one. So, and that is already less than, so we just do a direct table. So that is 0.9251. So remember, the table always gives less than. So if you need less than or left, you already have the answer directly from the table. If you need greater than or to the right, you have to do the 1 minus the table. All right, let's look at this one. It says find the area to the right of z-score negative 1.9. So again, we're doing to the right. So probability of z being greater than negative 1.90. That's going to be 1 minus the probability that we were less than. So that's what we get from the table. So negative 1.9 and then a 0, that's this. So that is minus 0.0287. So 1 minus 0.0287 is 0.9713. Now let's think about this for a second. If your z-score is a negative 1.9, let's just make sure this actually makes sense to us. Negative 1.9 on the number line of our bell curve, when we standardize it, is about right here. It's like right before negative 2. The area to the right of that is very, very large. Okay, so this makes sense. We have a lot of area to the right, not so much area to the left, which is why our left answer was so small. Okay, so remember, area is represented by probability. Okay. All right, now the last thing in this class section is the percentiles. Now I talked about this a little bit in class, but we didn't get to discuss it. If you take and find the z-score at a specific position and you look at the table, that would give you your probability to the left. That is actually how they calculate percentiles. So if someone's child has their height and weight measured, they take the height minus the average height for a child of that age, divided by the standard deviation of the child's group of people that are just like them, and then they give them a z-score. They look that z-score up in the table. That table gives them the percent of people that are to the left of you. That is called your percentile. So when someone tells you your child is at the 82nd percentile for height, that means 82% of other children in their gender and age group are shorter than them. They're to the left of them. Okay, so that's what the percentile tells us. A percentile is a term that describes how a score compares to other scores from the same set. We use to the left. Okay, that is always almost I know they say there's no universal, but that's the one that we use in America. And on standardized tests. So like the mean on a normally distributed exam is 71 and the standard deviation is 9.2. Joe earned a 52 on the exam. So we're going to turn her into a z-score first. So 52 is her score minus 71 divided by 9.2. So 52 minus 71 is negative 19 divided by the standard deviation of 9.2. Then we're going to round that to 2 decimal places. So that'd end up being negative 2.07. The 6 gets bumps up by the 5. So negative 2.07. What percent of those taking the exam scored lower than Joe? So we're wanting to know probability that someone scored lower than Joe. So to the left of her z-score. So we need our table, and I believe I could use this one. I left it on here because we needed it for this one. So negative 2. 0.0 and then 0.07. So negative 2.07. So that is this value directly right there, 0.019. Okay, I didn't call that out right. 0.0192. I knew I didn't get all the numbers. So let's change that to a percent. So we multiply by 100 or move our decimal 2 places to the right. And then we're going to round it to the nearest whole percent. So that's going to be approximately 2%. Now, that means that Joe is in the second percentile. Okay, 2% is the second percentile. 98% would be the 98th percentile. You just use the like numbering system. So like first, second, third, fourth, fifth, sixth, and so on. What that means is Joe only scored higher than 2% of the other people taking the exam. So she's in the lower percentiles. More people did better than her. Look how far she is below the average, okay? So Joe's at the second percentile for this test. That means 2% of her classmates scored lower than her. That also means 98% scored higher than her, okay? So that is how you work with a percentile. You take that z-score, you find the exact table value, because usually we're doing less than when we're talking about a percentile. We get it in percent form, and then that is their percentile, okay? So if she had been, if she'd made a 92 on the test instead of a 52, she would have been in a way higher percentile. If she scored exactly a 71, she'd be at the 50th percentile. You end up getting 50th because you get 0 for your z-score. So a person who's exactly in the mean is going to be at the 50th percentile. 50% are below them, 50% are above them. All right, that is the end of this set of notes. I will get this posted for y'all right away.